Welcome everyone, let's start. And as I said, this is not the first session. This is already week 4 on this road to Google Developer Certification. And my name is Rosa Castillo. I think I already mentioned at the beginning. I'm from Malaga, Spain. I'm a GDG organizer here and also Women Tech Makers Ambassador. Professionally, I work as a data scientist since many years. And I put there my Twitter handle and also my username in GitHub. Just feel free to connect and ask me any questions or whatever after the presentation. Cool. Next is what are we going to cover today? We are going to explain this journey, a little bit of the road to Google Developers Certification, where we are right now with this content. I will also introduce some concepts of the theory regarding connected with the exam that you're supposed to do. And we will review together some of sample questions. And finally, we will share some extra information, next steps for you to do. And that basically means homework. And there will be Q&A. I have, regarding questions, my beautiful and wonderful colleagues that they will be moderating the chat. So you can post your questions there and they will try to answer. And if not, I will try from time to time to check if there is someone asking something. And if not, in the end of the presentation, at the end of the presentation, we can cover them, okay? Where are we? This is the whole journey, and we cover in the previous weeks from the beginning fundamentals on Google Cloud and machine learning, and an introduction also to TensorFlow on Google Cloud. And last week they covered the feature engineering part and machine learning in enterprise. Today we are going to concentrate about steps or things important that you need to consider when you put your machine learning models into production. And what you see here, these two links, I opened them here. They are specific labs in Google Cloud. If you register for this event, you should have received an email with some credits. Like, for instance, this is my account. You see how many credits do I have. So far, this is the whole journey and the whole cover that we are having here. You can request some badges that you see here. This is skill badge thing that you see is for your Google Cloud profile, that is kind of recognition. And yeah, let's go and try to start covering what I presented today. For the exam guide, we will do the sample exam questions later. So in this particular week, what we want to discuss and maybe reflect a bit is about when you are developing a model in machine learning, which are the important things, the relevant things that you need to cover, right? So first of all, you need to find a solution to a problem, right? You need to know your problem, and then you build that solution, you build that model to solve it. And that after you decided to go for a solution, then you train that model. And when you are training that model, you need to pay attention on performance. So that should be your focus, no? Which is the hardware that do I have available? Is this model really requesting a lot of memory or a lot of computation? That all those questions, the answers to those questions will guide you in which is the best way to train your model. And you will have to test your model. How good is my model? You need to find or define a strategy to test your model. And finally, you need to think about the way that you will give away that model to your client or to your company, and how are you going to serve. And the term serve is the same as deploy, right? So how are you going to deploy this model? How are you going to keep it updated? And how are you going to monitor and maintain it? So all these questions, all these things are relevant when you are developing a machine learning model. So we can see all these also in a kind of a graphic way on where we can identify the different processes in the machine learning kind of flow, right, that you see here. And obviously the whole journey starts always with this part of data cleaning. That's the part that many people find very boring, but unfortunately that's very needed. And because reality is that most of the data that you will find out there, it will be messy, it will have missing data, and you will have to invest some time in putting everything nice and prepare for your model or your solution. So after that part of cleaning comes a process called feature engineering. And what we mean by feature engineering is a crucial, it can be a really relevant step in your machine learning model, because you need to transform sometimes your features, your input variables, into another format that maybe is more performant with the way you're going to train your model. And I can give you an example. For instance, neural networks, right? They need to converge, to iterate, to find a solution. No? So you can accelerate that conversion to a solution by the way you are scaling. If your input variables are very different, the ranges are different, then the conversion is going to take longer. So that's, for instance, a part that goes into feature engineering. Another thing that you can do in feature engineering is, like, imagine that you don't have enough data, so you don't have enough input variables. So you can create new synthetic features in trying to guess if this new feature is kind of connected or can give you more hidden patterns of the model of the thing you're trying to predict. So that's a very common thing that sometimes is done in feature engineering. Once you have done all this, the cleaning, the preparing all the parameters, the scaling, transforming, or creating new ones, you go to the part of building the model and start training it, and then finally deploying it. And after the deployment, there is this kind of iterative process that you see in the loop, because it might happen that you need to update, obviously, your model, and then maybe after the updates or after the feedback of the model, it could happen that you need to change something in the model, or even find a new strategy, right? So that part, as I say, is iterative, and this is kind of the whole picture that you need to consider when you are building your machine learning model. And when you are building the model, when you are training the model, there are two things that could happen. And I would like to ask you now, how many of you know about underfitting or overfitting? That will give me also an idea of how much you know already. So in this slide, what we are presenting is three different solutions for the same data set. So the data points in green color, what you see is kind of my data. On the x-axis, it could be the input that I I have in my data set. And then on the y-axis, you have the output, or it could be the target value, the thing that we want to predict. So what we're trying to do with my machine learning model is to kind of find a formula, a mathematical formula, that when I give some input, it will give me the answer. We try to predict the answer. And the different ways to do that is, for instance, if we concentrate ourselves on the third one, if I ask you which is the best formula, so which is the solution that predicts the best the output, right? So which is the solution from these three that is capturing all the variants, all the special cases of my data set? If I ask you that question, I know you should know the answer. The answer is the third one, right? The third one is the one that is really capturing with these, waves, all the little variances of my data set. So probably that model is going to predict the best from the three, the outputs, right? But then that's the question. That's what we want. That's what we want. We want a model that is just perfect for the input data set that we use for training. And the answer is no. Why? Because if I try to use this solution, this kind of very complex wave solution mathematically to predict in a new data set, in unseen data, probably that model is not going to perform well. It's not going to give me good answers because I try to optimize till the extreme the solution for this specific data set. And you want a model that is not only good for this data set, but on average and with other new data, it is also good. So that's what is called overfitting. It's like having a model with a high variance that it really is following every little, even noisy. You can have noisy data points. You don't want to follow noisy data points. And on the other extreme, we have the underfitting part, which with a model that is very, very simple. So as you see, it's just a straight line. So I could even create a model as an example for underfitting that is just giving always the same answer. Imagine that I ask you, okay, build me a model to predict the price of a house based on the number of rooms, the size, the location, and so on. And you come with a model that say, okay, my model is going to always say $500,000. No matter the input that you give is kind of a constant model. It will be just a straight line. That's a valid model, but obviously it's not going to predict well in most of the houses. In the houses that had exactly that price, it's going to be perfect. But for the rest, it's going to give you a very bad prediction. Why? Because you are simplifying too much. You are not capturing enough variance in the model with your model. So the right answer is in the middle, is this balanced graph, this balanced solution that is not so simple that you are missing most of the patterns of the data set, but also not extremely following all the variations of my model. And now comes the question how we fix overfitting, right? How can we prevent in our machine learning models that to happen? In this graph that you see here, what we are painting is something called the loss. Yes. So loss is connected with the error that I'm doing in my prediction, right? It's a mathematical formula where you are just subtracting the difference between your prediction from your model and the actual value of the model. And then you square that and you average and so on. In the end, what you have is a measure of the error that you are doing, right? So what you want is to have the minimum error. So you want is just to minimize the loss, to have a model that has the minimal loss in doing the predictions. And on the x-axis, what you see is iterations. It's iterations through the batching, through the training. So to 100 iteration, 200 iteration, 300 iterations. So it kind of measures if by iterating more through the batches and the training samples, my model is really improving, is really doing less errors by learning more from the data. And what you see here is two different data sets that were used to test the modeling. And one is with the trained data set, is exactly the data that I'm using. I'm showing the model to learn. And the other is something called validation. That is a different data set that is not used in the training, but you keep apart to kind of test or validate how well is my model performing. So as you see here in this model, this machine learning model, the loss for the training data set is going to the minimum. It's really reaching the almost perfection. But on the validation data set, it doesn't matter from the 100 iterations, it's not improving at all. It's like it's even going slightly high. So it's like not really performing well with new data. Ways to fix overfitting is adding something called regularization. Regularization are just parameters. So remember, in the end, we're talking about formulas, right? So loss in the end is just a mathematical formula. And what you add is just a component, an extra component where you are adjusting the input parameters with some with a lambda, right? So some specific regularization parameter. And by doing this regularization parameter high, what you do is that you force the inputs to be zero, to be low. And these two types of L1, L2 regularization are just two different formulas, two different ways of adding the extra parameter. And one is ridge regression, I think, and the other is the lasso one. And yeah, you by adding this penalization kind of mathematical thing, you are forcing the model to be like less good, right? So you are artificially saying that the loss is worse. So the weights that you're using in your formula to find the perfect formula to shape, they will be lower. And another technique that is used is this dropout technique, that is basically, instead of giving all the data points that I have in my training data set, it's just keeping some, not for training. So it's like hiding to the model some data so that it doesn't learn from that data. It doesn't capture all the variance in that data. And also in neural networks, dropout is another term used to drop out neurons in your network. You can have a neural network architecture with many layers and numbers of neurons. So there is also something called dropout technique. It is when your neuron is very complex and you want to also is doing overfitting or whatever, you can drop out some neurons while training to kind of reduce the complexity of the model. And that's exactly the final conclusion, reducing so you can add this regularization to kind of adjust the parameters to zero, the weights, or you can just go and say, okay, imagine that your solution is a polynomial, a mathematical polynomial. So it can have many grades, many high order grades. So one way of reducing the overfitting is to say, I'm going for a more simple model, I'm going for a more simple formula, I'm going to remove the high order components in my mathematical polynomial, for instance. That could be for overfitting, and for underfitting, it could be the opposite, right? So we are regularization, doing too much regularization. So instead of putting this lambda parameter very high, what we're trying to do is let's put it lower, so a smaller value for that parameter. Another way of improving is increasing the model complexity. As I said before, I put the example of just saying a constant prediction always. Okay, try to find something more complex, a really mathematical form, increase the orders of your polynomial or whatever in regression, for instance. And another way to improve it is with feature engineering. So it's like including new features, new ways of learning from the data. Maybe, as I explained before, from the data that you have with the input parameters that you have is not enough. So you need to find a way of creating new features. And I forgot to say here that, as you see in this slide, in an underfitting model, what you see is that the model is bad for all. So it's not predicting well, not for the train, not for the evaluation. It's just bad. So it does not improve at all with more epochs, because it's not learning, it's not capturing the patterns of the data. Good. So enough from the way of while training and what are the problems that you might encounter. And now we are going to concentrate about the way of distributing your samples, the way of doing the training. And in this specific process, you can apply to different approaches. One is the asynchronous parameter approach, and the other one, the synchronous or reduce approach. We are going to explain a little bit both of them. Let's start with the asynchronous parameter server approach. As I said, these are ways of, once you have your training data, you think about how I'm going to distribute this with computers, or in which architecture I'm going to start learning. And in the asynchronous parameter, as the name is saying, what you have is two different roles. You have something called the servers, the parameter servers, which are the blue squares that you see there. We have two here, and then you have the workers. In this case, we have 4 workers. So these workers are independent. They work independently. They receive a copy of the model. They start doing some training with some batches, and then when they finish, they pass the gradients to the server. Each worker, as I said, is independent. They always need to take the update from the server, and this works good. So it means that all the workers will receive at the beginning all the batches. But what could happen is that if you have, for instance, a worker or a computer that is faster, it's maybe more powerful than others, it could happen that ends faster than the others. So what you can have is unsynchronized, out of synchronization workers, because one is finishing faster the processing of the batches than the others, and is communicating with the server more often. So that can create also a bottleneck in the communication, right? So this configuration is particularly good when you don't have so many frequent updates, and more or less the workers are of the same kind of power computation. The way to solve this out of synchronization problem is to go for the synchronized or reduced architecture. So here we don't have servers. Here you only have the workers. It's the same configuration, but without work servers. These 4 workers, they need to synchronize each time. So it's usually used, this configuration, when you have powerful workers, and that was used especially with GPUs and TPUs. And before they train a new batch, they need to always synchronize all together. So there is always this full synchronization. And what they do afterwards, after receiving all their synchronization, is that they take each model. So each worker has created a kind of an updated model with a measure of the accuracy or the performance. And then what the reduce means here is that when you receive all the performance of all the models, in this case we will have like 4 kind of measures of this. You average them, you reduce that average to have an idea how well is doing your model. And this works also good when this configuration can be on the same machine, so not in distributed machines. So the question could be now, so which is the best solution, which is the best approach for me to take? It depends, obviously. It depends on which is your model, the ones that you need to train, and the computers that you have available. But here, few tips about how to decide is like the first approach, the one with asynchronous parameters, has been used for long, especially when you only have CPUs, not GPUs or TPUs, very powerful computers. So that's a good option. And you have also, as it's saying here, not so powerful workers, but it's a mature approach, has been used for a while. On the contrary, if you have very powerful machines, or you have available GPUs or TPUs, the synchronization or reduce works better. And it has they need to have also strong connectivity, strong connection. the workers. And the question about constraint is like, yes, if you are more constrained about your input-output communications, that you don't want to have so many, and then go for the asynchronous is the best. But if you're constrained by the computer powers, or you have more available power on your own, then go for the synchronous. It works better. We are going now to the explainability, and let me ask you, if have you heard before about more explainability? You know something in this particular case that sometimes it could be you forgot to say something about regulations. And some countries, they have specific regulations where you need to explain why your model is doing what it's doing or saying what it's saying, especially in insurance companies or in banking. So they are forced to do it. It's not optional. It's not like someone said, I didn't implement it. In some fields, in some business fields, it's not optional. You have to explain your machine learning model. And another very important thing, I think you already touched a little bit, is trust. So with explainability, what we want to gain from our consumers or the people using our models is that they trust the model. And that's a very, very important thing. How we do explain our model. I think maybe you have heard before about, not even before showing the next slide, the importance feature, right? Maybe some of you have ever heard about, there are ways of knowing from all the input parameters that I give in my model, which are the most relevant ones. And that's something called like kind of a local importance feature. And one way to understand it, for instance, is if you're building a tree classifier, so a random forest or whatever. As you know, when you visualize the random forest in each node of the leaf, it has a condition to decide if the decision will go to this tree part of this other part, right? This branch or this other branch. And the higher you go in the decision tree, the more relevant are the nodes, right? Because they decide the balance of a lot of prediction into one side of the other. So that's one way of seeing the relevance and of the random forest. But in this particular case, for neural networks or things that are more complicated to explain, like someone was already pointing out, there is something called gradient-based attribution. The way to understand is that I know you know derivatives from mathematics. Does the audience know how a derivative means? This, what you're seeing here in mathematics, is a derivative. Basically, it means when I change something on what is under the denominator, when I change something in xe, how does it change y, right? So when I change something in my some input feature, I isolate one specific input feature, I start playing with it, changing a bit, and then I see how the prediction is changing from maybe saying yes to no, if it's a kind of a binary classifier, or the classification of something else, like, for instance, image object recognition. In the case for linear models, yes, that's already covered in the so-called feature weights. So the weight that you give to a particular parameter of your linear model is the importance that you are giving to that feature, right? In the case, coming back to the prediction of prices of houses, it could be like you have an input that is the rooms, number of rooms, another inputs like the location, another input like the, I don't know, the number the pets are allowed or not in the house. And then the factor that you multiply, the number that you multiply for each of them, is going to say which is the more relevant, the more important for you. In the case for nonlinear models, it's used something, an approximation. It's like kind of manually or whatever, varying the thing. And the the example that we're going to show right now is applied to images. So in image recognition, what you're trying to identify in an image is an object, right? So what we are going to do is to play with the luminosity of the image, so that when isolating one pixel and then changing the luminosity of that pixel, you see how it affects the prediction of an object, right? The final, like saying there is an object here. And this can be used as a kind of a mask to that you can overlay that importance with I don't know, you put it like a number, black and white, and then you see that the parts of the image that by changing the luminosity on those ones, those pixels, then your model is predicting something. Okay, and in this example, what you see is like, as I was saying, you take the image. In this case, it's a kind of a sea or lake with a boat, and there is a waterfall, and there is a bridge, right? And some lamp too. So you start with the total black, all pixels are put to black, and then you start modifying the luminosity of the pixels, and then you see the variation on the score. The score is like something is detected or not. Okay, so what you want to see is that when there is the jump from not detecting any object to saying, oh, there is something here, right? And as you see, for instance, the scale image is what I say, is just applying changing the luminosity of the pixels. You are playing with the original image and changing the luminosity. And what you see below this as scale gradients is exactly those pixels that are triggering the score to 1 in which specific moment of the change of the intensity, right? And for instance, you see different stages, like in the first stage, the pixels that are coming the fastest is the ones from the bridge, because it's the darker part of the image. So that's the one that will come up as a first prediction, like, hey, there is something here. And then comes, for instance, later the water, because the water has a different luminosity. So when you you reach that part of the luminosity and start increasing that part, then you are capable of detecting. So by overposing this kind of images, in the end, you can show that your neural network, whatever prediction model, has identified these objects thanks to these pixels you see in the image that helped the model to say there is a waterfall there, or there is a lamp, or there is a bridge, right? So it explains why did you say that there is a bridge in the image, or a waterfall, or a lamp, right? So that's more or less. And now come the funny part. We are going to do exams. Yeah. Are you motivated? Are you prepared? First question. You need to write a generic test to verify whether a dense neural network models automatically, I try to help you, released by our team have a sufficient number of parameters to learn the task for which they were built. What should you do? So let's rephrase. You have someone prepare a deep neural network automatically, and then you want to know if that solution has enough parameters to learn. Okay? And the solutions, you have 4. First one is saying train the model for future iterations, check for not a number values, train the model for future iterations, and verify that the loss is constant. Remember what we said about the loss. Train a simple linear model and determine if maybe a neural network is better than a simple linear model. So it's just comparing 2 different solutions. And finally, if I train the model with no regularization, I can verify if the loss function is close to 0. I'm going to say the solution first. Ta-da! Is the D one, and I'm going to explain why. First of all, when you're doing any exam, it doesn't matter if it's the certification of Google or whatever. I remember that from the university. Always pay attention to the explanation, to the question, because there are relevant keywords that give you the hint to the right answer, okay? Before concentrating into the answers, just first concentrate on the question. If you pay attention to the question, it says, you need to prove that it has sufficient number of parameters. So first answer, it says, train the model for iteration and check not a number of values. Missing values, you're checking missing values. You're not checking if it's enough number of parameters. So that is automatically discarded. I'm glad that no one said that. The second one is again training and verify that the loss is constant. I guess you already knew that that's not right, because you want to minimize the loss, not to keep it constant. The third one, that was the tricky one. That's why some of you, because it's comparing if the architecture is complex enough, but it's not saying sufficient number of parameters. It's just comparing two solutions. It's not saying for this solution. So you need to say for the deep neural network, you don't need to say for a simple linear model. For this model that I'm giving to you, tell me if it has enough number of parameters. And that's why you need to check it first without no regularization. You don't try to adjust anything. Take the deep neural network, check it. How is the loss? Is going down or not? If it's going down, maybe it's enough as it was trained and is good. But if you say that it's not close to zero, then you start playing with regularization. But that's why the answer is D. Is clear, more or less? Okay, this was warming. Let's now go to the next one. You will guess this one, I hope. You work for a textile manufacturer and have been asked to build a model to detect and classify fabric defects. You train a machine learning model with high recall. I guess you know what is recall or not. Let's just remember. Precision is that if I'm saying all these are defects, how many of the ones that I said that are defects are actual defects, okay? That's precision. And recall is, I have in my data set all these defects. How many are you detecting with your model? Okay, that's recall. So it has a high recall, which is good. It means you're covering most of the defects. Thanks to high resolution images taken, blah, blah, blah. That's not important. Now, attention, you want quality control inspectors to gain trust in your model. Which technique should you use to understand the rationale of your classifier? The first one says use k-fold cross-validation to understand how the model performs. The second is using integrated gradients to efficiently compute feature attributions to each predicted image. C is saying use PCA, principal component analysis, to reduce the feature data set or the combination into a new, easily to understand features. And finally, the K means clustering, blah, 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 to group similar images together and calculate the something called Davies Balding index. I was not aware about that index. I have to look for it. I never used it. I have used clustering before. The real answer is B. And now let's review why. As I said, pay attention always to the question, what are the relevant words here? So here, relevant words is like you want to gain trust in your model. So you want to understand the rationale, the reasoning behind. Cross-validation, the first answer, that's not for understanding the model. That's just to give you an idea of the average performance of your model while you're training it. So you keep from the training data set some parts to evaluating each iteration, and then it gives you an idea in the end what is the average accuracy or whatever of your model. So it's not to explain, it's just for you for performance. The second one is connected with what we just introduced, is this integrated gradient methods to understand which parts of the pixels are giving us the information to say if it's a defect or not. So it was really connected what we presented. Why is not C? I know some of you fall into the trap. Principal component analysis is a unsupervised kind of technique or to reduce dimensionality. So it's like if I have, for instance, a problem with 100 features, I need to predict something using 100 features. So what you do in the end is to represent a kind of a space with which is 100 dimensional space. Try to imagine that. We can't. So PCA is kind of saying maybe from those 100 features, they are not equally relevant for your prediction. So let's try to get the importance and to reduce the dimensionality into something less than 100 dimensions that is easier for you to understand, maybe in 2 or 3 dimensions or less. But the problem with PCA is that you are losing explainability. Why? Because the 100 features are the ones that you can identify in your data set. Like, I don't know, imagine that is the genes components, and you have all the names of each 100 of the 100 features. But when you transform that into maybe something that is just 3 dimensions with the PCA, what is the first dimension? What is this first merge feature? You have no idea. It has condensed like 50 features into one. How are you going to explain someone? Well, that's a mix. This feature here that is the most relevant is connected with this, and this. You have no idea. It's mathematically is correct, but for explaining is the worst. No, you can't explain what is the new dimension after merging 3 or 4 dimensions from the original data set. So that's why I'm afraid it was not C. And the last one is just measure. It's like comparing if I am good clustering images, like images with effects and images without effects, but it's not saying anything. How are you? Why are you doing that? How you know that this point goes to the cluster of the effects or not to the other? It's not explained in anything in that. Well, you have a last chance. Let's try to guess the last one to guess it right. You work for a large retailer. You want to use machine learning to forecast future sales leveraging 10 years of historical sales data. And the historical data is stored in cloud storage in Abro format. You want to rapidly experiment with all the available data. How should you build and train your model for the sales forecast? Okay, you have 4 options. First one is kind of using BigQuery and summary model on BigQuery ML. The second one says it converts into a CSV format and create a regression model into ML. The third one is convert into the TF records, TensorFlow records, convert into TensorFlow records and create a recursive recurrent neural network model, blah, 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 and I platform notebooks. And the last one is converting a refactoring into CSV format and then building a XG boost algorithm, a platform training. Cool. And the answer is A. Why? Okay, again, pay attention to the question. It says you want to rapidly, okay? That's why I said it with emphasis on that part. You will rapidly. It's something that you want to do fast. You don't want to start converting, transforming, and doing all stuff. You want to really have a quick view of, okay, is this good or not? And then it says also that is for forecasting, okay? So the first question for me, it was like attractive at the first sight, because it's like you just load the data into this BigQuery thing and you use an ARIMA model. I don't know if you have experience with forecasting, but it's a very common approach of modeling the time series and getting to know the autocorrelation between the samples. So for me, it sounded like a valid one. And it seems that it's kind of automatic, already given, available in BigQuery ML. Why the B is not good or the D? Because both are transforming into CSV format. And if you start transforming, then you don't have a quick view. You need to spend time transforming the data into that. So that's why these two are kind of automatically discarded. And the third one, that's the one that you got trapped, is because it says into, okay, TensorFlow records, that transformation I can buy that thing. But in the end, you are creating a neural network model, which is more complex to build than rather select a automatic ARIMA model from this BigQuery ML. So it will take you more time. So that's why I was focusing on the rapidly experiment. So C could be a valid answer if you didn't have the rapidly thing saying that you should get a quick thing. I don't know if it's all clear, but I think that's the last thing we had to show today, and I think there are, well, we have time for questions, and the badge that you can claim that, as I said before, I think maybe I can copy the link address. If you don't have it, just, it's nice always to have badges. And that's it. I mean, that given said, there is also this community dev website, and I hope that you enjoy it. And I stop presenting, and that's all. So thank you very much. Have a nice pre-weekend, and hopefully see you next week.